Okay, so integration day 9, integrating absolute value functions and piecewise functions and the average value of a function. So there's 3 things we're going to talk about today. Kind of like absolute value and piecewise together. And then we're going to talk about the average value as another group. So if somebody asks you to find the area from 0 to 3 of x minus 1 dx, I guess the easiest way to do it is to throw it in your calculator. And then you go math, over to num, down to abs, x minus 1, and I don't know. Well, you better go up to 3 at least. So then we hit graph and our calculator shows us this shape, right? And you ask it to find the area from 0 to 3. Second, trace, 7, 0, enter, 3, enter. And watch how the calculator does it. And it's drawing it from left to right and coloring it in, so it gives you an answer of 2.5. Yeah? So the area, the total shaded area is 2.5 units. The net area is 2.5 units. They're the same because they're both above the x-axis. Because all the shaded area is above the x-axis. Good? Okay. So you could draw the little picture over here, and you get the same thing. If I could draw, you'd be really happy with me. But absolute values are piecewise functions. There's a part with a negative slopey bit, and there's a part with a positive slopey bit. So what we actually need to do is, if I asked you to do this algebraically, so I kicked you in the shins and took your calculator away from you and said, find the area, you need to see that those 2 lines can be written. There's actually a really easy way of writing the lines. The first line, or the one on the right, can be written using the equation y equals x minus 1. The one on the left, it's got a negative slopey bit. It can be written using the equation y equals negative x minus 1. Because what do absolute values do? They change positives into positives, and they change negatives into positives. Well, how do you change something that's negative into a positive? You multiply by negative 1. Because it's really drawing this line down here. Think about all math 12, and then it's sproing it up. So how do we sproing something up? We throw a negative sign in front of it. Okay. So how do we get it to do the area on the left? Well, we're going to do, or the first half of the area, it's not really half, but the first part. We're going to do the antiderivative from 0 to some number of negative x minus 1 dx. And then some number, I'm asking you to figure out what number that is. And then we're going to do the antiderivative from that same number to 3 of x minus 1 dx. So I'm asking you, what is that number right here? And how do you know where it is? Okay, yes it is. And how do you know that? Yeah. It's the 0.10. So you need to find out where you go across the x-axis. Stupid x-axis. What is it? Ugh. Anyways. Good? Yeah? No? So you got to be careful with absolute values. You got to watch for where it sproings, because you got to break it up. Okay? Okay. Example 2. Evaluate the following integral and give the graph of y. Okay. So I want you to find the shaded yellow area. Do you want to do total or net? Total? Well, we can do both at the same time. Total. Total area. So to do this algebraically, it's actually a lot of work. you would have to do the area from negative 3 to 0 of f of x dx. And then you would have to do the area from 0 to 1 of f of x dx. And then you would have to do the area from 1 to 3 of f of x dx. Plus you'd have to do the area from 3 to 4 of f of x dx. And then you would have to do the area from 4 to 5. And then you would have to finally do the area from 5 to 6. So do we hate piecewise functions? Now why am I breaking it up at those points? There's two reasons why I'm breaking them up there. What? That's where it cuts the x-axis. Also, where it corner points, where it changes. So whenever you cut the x-axis or change corner points, you need to write another integral statement. A lot of work to do, isn't it? Now, if you look at those four shapes, there's 3 shapes there. It's actually really easy to do it a la grade 9. The first shape, Mr. F, is a triangle. I can find the area of a triangle. Base times height divided by 2. So, base times height divided by 2. 3 times 3 is 9. Half of 9 is 4.5. And then, Mr. F, that second shape is a trapezoid. How do you find the area of a trapezoid? The area of, no, that's too much work. It's the average area of the bases times the height. Sorry, the average lengths of the bases times the height. So, from here to here is 4. From here to here is 2. 4 plus 2 is, the average of that is 3 times the height 1. 3 times 1. Now why the heck is he adding 3 rather than minusing 3? Because you said total, Mr. F. Oh, that means that I would have to take these ones right here and remember that it's going to give me a negative answer, so that I'm going to have to add them all together and then change the sign and make the positive. Yes? Okay, and then the last shape, Mr. F, it's a triangle. What's the base? 2. What's the height? Well, what's the area? 2 times 1 is 2. Half of 2 is 1. So the total area is 8.5. What's the net area? 2.5? 2.5? Because that plus 3 is actually a minus 3 when you say net area. Okay? So piecewise function, you got to watch. When do you cut the x-axis? When do you hit the corner points? Right? Okay, flip the page. Mean value theorem for derivatives. What is the mean value theorem for derivatives? Holy, you got it memorized? That's awesome. F of B minus F of A, and that equals some point C So the mean value theorem for derivatives says that there's some point C that has the same slope as the average slope on the curve. Yeah? And a whole bunch of things need to happen, right? It needs to be continuous and it needs to be differentiable in that interval. And B has to be to the right of A. But those are all technicalities. But what we're trying to get across to you is the mean value theorem is average slope has some instantaneous slope somewhere. Okay? Here's the mean value theorem for integrals. It's a little bit different. So what it's saying is I'm going to draw the picture. I guess I don't need to do it like that. You know what? That doesn't really matter. Okay. So, would you agree that if I do the antiderivative from A to B, it gives me the area from A to B? Yeah? And then I'm going to pause and ask you to think about something. If I had 20 kids in the class and I wanted to know the average mark, what would I do? Okay. Would you? Okay, good. Add them all up and divide by the number. So what you need to do is visualize. Do you think there's some sort of average thickness to this integral? Average thickness to this area? So the area from A to B is okay. And the way we find the average integral is add up all the marks. Here's the way you think about this, and you guys did it perfectly. This means add up all the marks. This means divide by the number of students. And we call this the average. The mean value theorem for integral says that there is some point C that is the average mark for the average student. And that point C happens to be on this picture, I would argue, maybe right around here. It's got the average thickness. So it's, now here's my cheesy metaphor, and it's not cheese, and I apologize to anybody who doesn't like peanuts, but here we go. Ready? So it's 3:30, you go home and you're hungry. What does Mr. App do? Takes his favorite multigrain bread, puts it in the toaster, it toasts, and the toast can be identified by starting at point A and finishing at point B. Nice good slice of bread. And he takes a spatula, no wimpy knives for me, takes a spatula, goes into that jar of crunchy peanut butter or raspberry jam, whatever works for you, takes that big scoop of raspberry jam or peanut butter and slams it on his toast. And it makes a curve that looks like what we see on our screen. Now, Mr. App's going to spread it out because nobody wants uneven layers of peanut butter on their toast. Anybody? Who slams the toast on the peanut butter and then goes, oh, you got to spread it. You got to spread it out, right? Now, I'm the nerd. I am the nerd that will look at the slice of peanut butter and toast and peanut butter and go, the average thickness is about here. So if I take this little chunk of peanut butter and I take it and I squish it over here, then I have created a uniform thickness of peanut butter. So what I'm interested in is where is that point C on my peanut butter toast before I start spreading it out? Because all I really have to do is take the little high points and put it over on the low points and I'm finished. The average thickness. Okay? The mean value theorem being applied to peanut butter toast. So when you go home tonight and you have your piece of toast, or you could do little mean value theorems, you could do crackers. Okay? A and B could be really close together. You could use a cracker and do the same question. And I want you to turn the cracker on the side and look at it and go, there's the average thickness. And I can take that little bit over there and put it over there, and I can find that point C, and we're all happy. Do you get the metaphor here, though? It's really cheesy for me to use peanut butter toast as the metaphor, but it's really easy to see it if you actually... Are we all hungry now? Well, not with peanut butter toast. Yeah, no, not... Okay, raspberry jam. Okay. What? Well, you could cut the bagel. You could cut the bagel and just look at a uniform rectangle of bagelness. You could do it. You could do it with a whole bunch of slices of bagel. Yeah, and then you could do it like 18 times. You could have 18 little mean value theorem calculations. That would be awesome. Or you could cut it and spread the bagel out and coil it into a long rectangle, and you could make B minus A really far apart. Okay, find the average value of the function in the interval 0 to 2. Okay, so what we're saying here is we've got a function. So here's my peanut butter toast. It's starting at 0, and it's going to 2, and I slam the peanut butter on my toast, and it looks like that. I want to know the average thickness of my peanut butter, or raspberry jam. So we use the average formula, and we go 1 over 2 minus 0, average, the antiderivative from 0 to 2 of 3x dx. So 1 over 2, 3 over 2, x squared, 0 to 2. Anybody notice that we don't need the plus c? Have you noticed that in chapter 5 we don't need the plus c? Pourquoi? Because it's always canceling. Don't need it. Chapter 6 you need it. I'll cut your fingers off in chapter 6 if you don't put plus c on the end. Chapter 5 they cancel, so you don't need them. So substitute 2 in for x, substitute 0 in for x. Mr. App, this peanut butter toast has an average thickness of 1 times 3 times 2 times 2, 12 over 4. It has an average thickness of 3 units. My peanut butter is on average 3 inches thick. What do you mean, ooh? Yes, you can. You big glass of milk. And then you could drink it. Then you could drink it, and it's a related rate question with the milk pouring out of the cylinder. Who knew? Who knew there was that much calculus in a snack? Look at that. That's a cylinder. It's a related rate question. Okay, now, what the mean value theorem says, okay, if your average thickness is 3 units, we could find that point C. Well, if the average thickness is 3 units, it's 3x equals 3. So at the point x equals 1, you don't have to move the peanut butter. No peanut butter movement required at x equals 1. Okay? Isn't that exciting? Only for you, Mr. Epp. Okay, number 4. We're going to do this sans calculatrice, avec calculatrice. Find the average value. Average equals 1 over ln3 minus ln2. The antiderivative from ln2 to ln3, e to the 3x dx. Well, there's 2 ways of doing it. You can use the nint button, numerical integral, but I don't want to do nint. I just want to graph it. It's easier. So you put e to the 3x, e to the 3x in your y1, and then you go second trace 7, and you go ln3, lower limit or upper limit? Lower limit, ln2, ln2, upper limit, ln3. This is so exciting because you know what? It's not every day when you put your peanut butter on your bread it looks like an e to the x function. Let me tell you. Colors it and says, hey look, that area is 6.3 repeating. So it's 1 over ln3 minus ln2 times 6.3 repeating. So you just use your calculator. One divided by bracket ln3 minus ln2 times, oops, close bracket, times 6.3 repeating. Now be aware, all you AP exam students, that thou shalt round to 3 decimal places, not 2, 3. So make sure that you're using enough precision. Is that enough precision, Greg? Greg's good? Okay. 15.620 would be the correct answer. So the peanut butter has an average thickness of 15.620 inches. Well, or millimeters, depending on what units you're using. I would probably use inches because, you know, you can never have too much peanut butter on toast. Amen. Are you picking up what I'm laying down? Yeah. You're going to go home tonight, your mom's going to say, what did you learn about? Thickness of peanut butter. Do not eat peanut butter unsupervised, Dylan is quoting. Okay. This one is just, okay, it's off an AP exam, but if you think about what this question is telling you, it's actually not very difficult. The question tells you that the curve starts at 0, and it goes to 2, and it varies between the numbers 2 and the values, y values of 2 and 4. Now, it doesn't tell you exactly what it's doing between, but it's going between 2 and 4. So maybe it's doing this. I don't know what it's doing. But it really doesn't matter. What's the biggest this area could be? And just stop and think. What's the biggest the area could be? 8. Right? It's this rectangle. It could be 8 units. What's the smallest it could be? No, not 0. No. What's the pink color area? Yeah. 4. Hard? Like you look at it and go, wow, that's technical. Really, it's just saying what's the biggest rectangle you could put around something? What's the smallest rectangle you could put around something? Right? Okay, the theorem then. If you have a graph that goes from A to B, and the lowest the graph gets is little m, and the highest the graph gets to be is big M, what's the biggest the area can be that's contained? What's the smallest area that could be that's contained? Good. That's the biggest it can be. What's the smallest it can be? There you go. Ba-dee-ba-dee-ba-dee-ba.